Okay, I hope everybody had a bit of a break. Welcome back. This is module 5.3, where we'll talk now about a little bit more about how to do antimony modeling and then how to integrate antimony modeling with CompuCell. And it would be useful if people could have the code that we were just running before. There are also a couple of other demos that we'll use, although they're all simple enough that you could write them from scratch in only a few minutes. As always, I need to remind you that this session is live streamed and recorded and is distributed on YouTube. And also, we want to thank our funding agencies, National Institutes of Health and the National Science Foundation, for their support. So today we're going to be talking about some of the issues that we face looking at antimony as a language. It's not a programming language, it's a model specification language, and there are some differences that are obvious about that and some that are subtle. We'll talk about functional assignments and time-dependent relationships, a little bit more on debugging antimony, some of which I think I already talked about earlier, and then how to connect antimony to CompuCell, how to run stochastic algorithms using antimony in CompuCell, and how to do antimony events, which somebody asked about earlier. And then I'll show you a little bit more about how the connections work between the two. So I'll give everybody a minute or two to get loaded again and ready. As always, we have these great resources. There's the Antimony Tellurium cheat sheet, which has the basics on it. There's the online documentation for Tellurium and antimony, which is great. Has lots of demos and code that you can use. And there's Herbert Sauer's nice textbook, Systems Biology, Introduction to Pathway Modeling. And some of his other books dive into more detail about some of the specifics about modeling specific systems, whether it's gene regulatory networks or metabolic or signaling networks. I'll remind you of the basics of antimony syntax, which is very simple. The fundamental concept in antimony is a chemical reaction, or just a reaction. That is, something is transformed into something else. You write X goes to Y. That writes a pair of differential equations, one that destroys X and one that creates Y, at a rate specified after a semicolon. If I want a backward reaction, then I need a separate arrow for it. And I could write arbitrarily complex chemical reactions this way, and antimony will automatically take care of the bookkeeping of what's called stoichiometry. Hash or double slash are the comment characters, semicolon is the delimiter, colon indicates a named rate law and makes the rate available. And you can also write ODs directly with the apostrophe, if you like, although we won't do that much here. I want to talk a little bit about some of the subtleties of antimony. It is a declarative language rather than a procedural language. It may look like computer code, but it is not computer code. It's a model specification. And languages like systems biology markup language are also like that. And if you think about it, biology is like that too. There are no loops or if statements in biology. Things happen simultaneously. Doesn't mean you can't get things like oscillations or decisions, but those are a result of the action of microscopic processes that are happening simultaneously. So an antimony model, as you know, is specified in a model string. And that model string then is loaded by CompuCell and converted to executable code. And what that means is that if we change the model specification, it's only changed when the model is loaded. So that means that if I change something in the model string and I don't reload the model, I will be executing the old model string, not the new one. Another thing that's unusual about declarative languages compared to procedural languages is that, with a few exceptions, the order of statements doesn't matter. In a procedural language like Python or C++, if you reverse the order of two lines, in general, you get a different result. In a declarative language, with some limited exceptions, that's not the case. Now, the parser does, in fact, parse the model string in order. And so if I have model string A equals 3, B equals 5, and then A equals 10, A will be left with the value of 10 because the parser executes its reading of the string sequentially. Similarly, if I accidentally give two rate laws the same label, E1 and E1 again, only the second one will be read. We saw that a little bit in the initial condition generation in CompuCell, where if we had two blob initializers, the second blob initializer wouldn't replace the first one, but would overwrite it in the cell lattice. We've noticed that Python has two kinds of equal sign and an assignment which changes the value of the thing on the left, and a comparator double equals that checks if the thing on the left and the thing on the right are equal to each other. Declarative languages also have a third kind of assignment because they have to distinguish when assignment occurs. In Antimony, equal sign is only evaluated at parse, and colon equals is reevaluated continually during the execution of the simulation. There is a big advantage to this, which means that we can load a model specification from Antimony and then change values from outside of Antimony. That's very convenient. However, it does mean that the regular equal sign doesn't update if a value on the right-hand side updates. So, for example, if I write the code A equals 0, C equals 3 times A, then C is going to be 0, 3 times 0. And if I then later change the value of A, C will stay 0. And that isn't always what you want. In particular, if you want to do things like scaling of relationships, that's not so convenient. And so Antimony has something called functional relationships. So let's look at those in two parts. First, the one with a regular equal sign. If I write K2 equals 3 times K1 and K3 equals 3 times K2, and I set K1 equal to 1, K2 will be 3, and K3 will be 9. When I parse, when I load the model. However, if I change the value of K1 going forward, I'll have a new value of K1, but K3 and K2 and K3 won't change. That means that the order doesn't matter. I could write K3 is 3 times K2, and then K2 equals 3 times K1, and then K1 equals 2, and I'll still get the correct values. In a procedural language, typically K2 wouldn't have been defined, and so Python would tell you that there was an error, and probably throw an error. Most languages would set K2 to 0, and so I'd wind up with K3 0, K2 0, K1 2. However, in Antimony, I'll always get whatever order those statements are in, I'll still get 2, 6, and 18. The only time that doesn't work is if I assign K1 twice, and then it'll use the last one that I define. Again, changing the value from outside will not change the value of the things that are dependent on it. I also am not allowed to write something like K3 equals 3 times K3, which is allowed in general in procedural languages, because the parser won't know what the value of K3 is. That'll generate an error. So antimony uses what's called the functional relationship, which is colon equals. It's a dynamic functional relationship. And that tells antimony at every time step, check to see if whatever is on the right-hand side of the equal sign, the colon equals, has changed and update it. So if I write K2 colon equals 3 times K1, K3 colon equals 3 times K2, K1 equals 2, then if I change the value of K1, the values of K2 and K3 will change dynamically. So the first exercise is something, take the little simulation that you have already. A goes to B at a rate K1 times A. B goes to nothing at a rate K2 times B. Set K1 equal to 0.2 and K2 equal to 1. And just run that. There's a version of this online, which you can pull, but typing it by hand isn't very hard. The code that we need, actually, I put in an extra. I put in the next step of the code here. Let me put it back to the way it was. Equal to 0.2. Okay, somebody says they see decay of A and B. That's good. Okay, so this is something we actually started with. This was the first simulation we started with at the very beginning. And you should get something that looks like this. Maybe the time step is a little big, so I should have made K1 0.02 and K2 0.1 instead. Be a little easier to see. But for now, we'll leave it the way it is. Now we're going to use a time-dependent relationship. And so we're going to make K1 modulated by a time-varying sinusoidal external signal. And we have to remember the time in antimony is time, T-I-M-E. And so I can do this here. And actually, that's what I had already in the code, but when I loaded it on the screen, I use colon equals, and I'll say the rate is 0.2 plus, and I'll do sine of time. Okay, try that and tell me what happens. And I do think it'll probably be a little bit more interesting if you slow things down a little bit. So maybe make make the parameters 10 times smaller than they were. It'll just doesn't really change the demo, but it makes the display a little prettier if you do that. Okay. People see that? Give that a shot. You'll see the results rather different, isn't it? What did you get? Somebody says oscillating in the beginning. Great. Okay, you should get something that looks a little bit like this. Now, one thing that's a bit of a problem with doing this, and we haven't talked about how to change parameters from CompuCell yet. We'll do that in a few minutes. Is that once I've assigned K1 to be on the right-hand side, the left-hand side of an assignment of a dynamic assignment, I no longer can write to it. I can read it, but I can't write to it. I'll find that that's true of those J1s as well. The J1 values I can read, but I can't write because they're a consequence of the value of other things. They can't be overwritten. It's a little bit like in CompuCell, I can overwrite the target volume, but I can't overwrite the volume of a cell, because that volume is a consequence of the simulation, not a parameter of the simulation. Okay. So that's something that we can do, and we do that fairly often. If we have a sinusoidal driving function, we can also play some other interesting games with that. We could have, instead of having, one thing you might want to do here, it's actually, you have to rescale things a little bit. While I'm talking about other things, you might try make K1 equal to sine of 100 times the value of A. See what happens. Anybody want to try that? Tell me what happens. Just the way when we do plots, we tend to think about plots with the x-axis being time, but there's no reason we can't plot one variable against another. In the same way, we can have a parameter depend on a function of another parameter or variable. Oh, it crashed? It did? Did it crash for everybody? Never changes. Okay, well, maybe I picked a bad one for that. It shouldn't crash, I don't think. Yeah, so I probably have to be more careful in my choice. Yes, well, I haven't run this, so yes, it better be A and B. Okay, great. So Marcella says that it using sine A works, so maybe it's the 100, the factor of 100 that made it wrong. Somebody tried 10 times. So, no. So there's a lot one can explore here. Again, for today, I'm teaching you syntax. We're not going to really have a chance to explore all of the, still works, but the curves are all apart. So I guess I can try it. Let's see what happens if I try it. Yep. Seems to reach a steady state, doesn't it? Not so interesting, perhaps. At least my axis labels are right now, even if the shape's not so pretty. Okay. So you can definitely play more with that. Yes, if that's the case, I haven't here, if the rate constants become negative, my game that I want to have my restrict values so that they can't go negative no longer applies. So mass action doesn't work with negative rate constants. There's some other games that you can apply when you're doing dynamical systems, by the way, which are sort of fun. To find unstable fixed points, you change the sign of time, you make time run backwards, and then all the stable fixed points become unstable and vice versa. It's a simple trick for finding unstable fixed points, but that's a little more than we can do in an afternoon. Okay. There was a question earlier about what Antimony calls events. What if I want a condition to happen and I want something to change? I want to imagine that, for example, at a given time, I add a drug or I give a nutrient, or add a nutrient at a given time, or something else changes in my system. Well, Antimony lets you do that. Now in CompuCell, we're going to be calling Antimony from CompuCell Python. And so quite often we're going to want to control things like events in CompuCell Python. Something happens to the network because something happened outside of the network. And in that case, we won't do that internal to the network. One principle which I did not talk about very much, which I should probably make some slides on, is that you should really try to write your components of your simulation, for example, your Antimony models, so that they can be run independently of the CompuCell simulation that they live in. So, for example, if you have a model of the replication of a virus inside a cell, you'd want to be able to run that model by itself before you put it into a cell to have it work. And in those situations, you might very well want to be able to have events happen inside the network. It's also true that within the cell, and these networks are really describing what's happening inside the cell, there are changes. You go from cell cycle A to say S phase to G1 or something like this, G2 to M phase. And so you might very well want to be able to have events happen inside the network. Those events could change the values in the network, or they could change parameters or variables, or they could change network structure. Antimony has a very, very simple syntax. Like everything else, it's very simple. It's limited in what it can do, but it's often enough for events. And the syntax is here on the screen. There is a label for the event. It's not required, but it's useful to have it. There is the word at, A-T, and then a logical expression. At time greater than 15. And then a colon. And one can argue about whether it really should be a colon or a semicolon, but it's a colon. And then the consequences of the event. And you can have multiple consequences for the same event, separated by commas and ending with a semicolon. So here, as an example, if I want to add 15 units to the concentration of A at time 15, I write event 1, colon, that's optional, at, not optional, parenthesis, time greater than 15, my condition, colon, A equals A plus 15, semicolon. Now you could say that seems to violate my rule that I'm not allowed to have a parameter on both sides of a assignment. The answer is I'm not allowed to have a parameter on both sides of a functional assignment, but I am allowed to have a parameter on both sides of an equal sign here, because that's only evaluated at the time that the event becomes true. And I could have A equals A plus 15, comma, B equals 3, comma, C equals C over 2. I could have a long chain of these. Any questions about that syntax? Now, because the logicals have a limited structure, sometimes you have to use some ingenuity, max and min functions. You can use random numbers in them if you want. You can use sines, cosines, basically all of the standard mathematical and functional operators are available. If you look in the manual, you can see the whole zoology of different possibilities. Okay, so let's take our simple example, set K1 back to K1 equals 0.2, get rid of the functional assignment, and then say at time greater than 15, A equals A plus 5, and run it and see what happens. Okay. So that's our little exercise. And if you forget to get rid of that colon equals, you'll get an error. So if I were going to be really technically correct, I should probably create a comment block and say events and then put my events underneath. I'm not going to be that fancy. I'm just going to type what I wrote, and you're going to have to tell me what you got. So there's a question about triggering, and I have a slide specifically on this. So triggers, so you could say, well, at time 15, the event is true. At time 16, the event is true. At time 17, the event is true. At time 18, the event is true. So why doesn't A go to infinity? Because it should be true, 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 true. And so I should just keep adding 5 over and over again. Well, that isn't what we would want it to do. And so the answer is that the event happens whenever the trigger goes from false to true. Now, in the case of time, the time isn't going to go back to being less than 15, so it's only going to happen once. But if I ask the question, if I wrote something like, if the sign SGN, actually, let me not do it that way. If sign SIN of time is greater than 0, colon, such and such. In that case, every time I get to go from sign of time being negative to positive, the event will trigger. The time stepping of the SBML or the antimony functions at the moment is not something that is controlled here by the event. A good thing to notice, though. Right. Yeah, sine of 10A times time would be an example. Yes, you can trigger on that. So this actually, so Darshan asked, will this trigger once at time equals 16? Actually, antimony will microstep the time. I don't remember exactly what the microstep is. It's less than 1,000th of a unit. And so it will trigger at 15, or as close to at 15 as its microstep will allow. And so essentially, you'll see the jump will happen at 15. Because we're only displaying once every Monte Carlo step, and we've got one Monte Carlo step set to be one time unit in antimony, you'll see it jump only every one Monte Carlo step. But if we ran it continuously in Jupyter Python, you'd see it would jump at 15. Okay, I probably have things stretched by 10 then. Let me check. See, this is the kind of thing I was concerned about. Let's see. Yeah, no, it should be. In mine, it's what is it? I've got a time equivalence of 1. Probably in the demo that I gave you, I stretched out the time to be 1/10. That's right. So yes. So I was going to come to that a little bit later. Yes. So what happens is, and we'll review this in just a minute. CompuCell will remember that CompuCell interleaves time steps. It moves the cells around with the GGH CPM algorithm. Then it runs the diffusion solvers. Then it will run the antimony solvers, the tellurium step. And I have to tell it how much tellurium time to use per call. Yes. If in line 28 in the version you have, it says time step equals 0.1, that's where that comes from, yes. And again, I'll come back to that in just a minute. So this is what I get when I run that. And you'll see in my case, I had equivalence of one. One Monte Carlo step was equal to one antimony time unit. And so for me, it really does jump at 15. Okay. So why don't we try that example at sign of time greater than 0.5? And here I said set B equal to B plus 0.5, but you can do what you like in terms of that. Does somebody want to try that? Does that trigger multiple times then? Do you see it spike up multiple times? People can play some fun games with this, I hope. Try out some different things. Yep. Comment was that if you make A jump up to B periodically, then it keeps B almost stable. This kind of decay system acts as a filter, a temporal filter. It's a low-pass filter. And so it actually will average out those sinusoidal fluctuations. There was a question, writing K colon equals 0.2 doesn't throw an error. Well, it shouldn't throw an error here. It will only throw an error if you try to change the value of K1. So if you write K1 colon equals 0.2, actually, it's interesting. I don't know if you sign it equal to a constant, the parser may turn that into an equal sign. Somebody says the period of oscillation seems to be around 65. It's basically because the period of oscillation is 2 pi times 10. So yes, this is like a delta function. I'm giving a bolus of A at a fixed time. That's right. If I wanted to model absorption, I should probably have a compartment in my model that describes, say, the stomach. I add A to the stomach, and then it exponentially is transferred into the bloodstream. So then B would be the dose of A in the bloodstream, for example. For such a simple thing, it allows you to play some fun games. But one does have to, we tend to think procedurally about processes. And again, I don't know how many people have done event-driven programming, which is not the same as object-oriented programming. If you do device control, for example, Peter says he's done event-driven programming. You have to think a little bit differently. Sharon says a lot of it. Of course, if you're doing control GUIs, you do a lot of event-driven programming. It does require a little bit of a different mindset, because in procedural programming, you expect things to happen in order. In event-driven programming, you're waiting for an event to happen. It may or may not happen. If you have multiple events, they may happen in different orders. And so another, Shilai says also event-driven programming. So it does require, as you know, when you started doing it, if you can remember that far back, you do start having to think about problems differently. When you're going to solve a problem using event-driven programming, it's a bit of a different set of concepts. Biology is much more event-driven than it is procedural. And so if you've done event-driven programming, building biological models will feel much more natural than it will. Things happen simultaneously in biology, and they're events. And both of those things are not things that come naturally to procedural programming. Would this help us to simulate homeostasis? That's a great question. Certainly events are critical to homeostasis. Entering the cell cycle or leaving the cell cycle is an event. Cell death is an event. Cell division is an event. Cell differentiation is an event. Those are all triggered by a whole variety of situations. And so fundamentally, we need to start thinking about again, this fundamental question when you're designing a biological agent like a cell, what information is available to that cell? It's easy to write a simulation that will do what you want it to do on the output side if I can have the cells have any information at all. Pedro joked about teleport as a function. Well, if cells could teleport, different processes could happen. If cells knew what was happening as far away from them, they could do things. One of the things that's very interesting about a structure like our hand is there's no blueprint. Cells only have local information. A given cell has access to its local environment and its internal state. It doesn't know what's happening a centimeter away. It doesn't know that it's located at its given position in the hand. And it's actually very hard to design self-building, self-assembling systems and self-repairing systems, which only have local information. And one of the great challenges in biology in building these models is actually building situations that respect the information that's available to a cell and that generate stable patterns. It's not so easy. So yes, absolutely, events are critical to almost everything that we're going to talk about. Now, again, a lot of the times the events we'll do in the Python layer CompuCell rather than in the Antimony. But it's important to know how to do it here. So let's take our trigger, and instead of triggering on time, let's trigger on the value of A. We'll let A go down. And when A reaches some minimal value, let's say 1, we'll change the sign. Instead of A being turned into B, we'll have B turned into A. We shouldn't really do that. It doesn't respect some of the rules of design. And if we're not careful, we could have this system could blow up. So if it crashes with a numerical divergence, just say I warned you. But try that. So instead of so now we'll say at A less than 1. And now we'll switch the sign of the parameter. K1 equals minus K1. Try that. What happens? Actually, I've cheated because I've already shown you the result, but make sure that that works for you, okay? Because time by itself is not something that is available to biological systems. Biological systems can't measure the time. They don't have clocks. They can approximate a clock. No, I don't believe you can, Darshan. Darshan asks, can we use colon equals within events? The event trigger is evaluated continually, or at least at the microstep of Tellurium. And the update is done every time the event goes from false to true. So you don't need a colon equal because this is not something that's parsed. The event specification is parsed, but the evaluation of the event is done dynamically. So effectively, the equal sign here functions is called repeatedly. So you wouldn't want to use a colon equal there. I don't know whether it'll generate a syntax error or not, but it won't do what you want. So did people able to change that? If you said at A less than 1, K equals minus K1. And I've got the picture already on the plot, goes up. So now I've said, somebody said you got an error. If you run it for a long time, it'll get an error because the value will keep going up. It can diverge, which is why I didn't make that an exercise. It was just an example. Okay. So now here's the exercise. Now make a K1 change sign when A is less than 1, and make it change sign again when A is greater than 8. And when you create a new event, remember to give the event a different label. If you give it both E1, it won't work. So what happens? And this is a clear example of the resetting, which is that the events happen when you go from false to true, not when you go from true to false, not when you stay true, not when you stay false. And I better not make it greater than 1. It'll get confused. One thing you do have to be a little bit careful about in antimony is that if you have two events that trigger at the same time, they should both act. And if they act on different parameters or variables, they will both act. But if you have two events that act on the same parameter or variable, you have a problem, because there's a collision. If you're used to event-based programming, this is a collision. You're trying to have two things writing the same variable at the same time. You can't do it. And so you have to have a conflict resolution. And one of the conflict resolution mechanisms would be to ignore one of the two. The other one would be to pick randomly and execute them in different order, random order. Another one would be to always execute them in the order in which they occurred in this parse string. Antimony is not always well defined in terms of what it does. In fact, I believe it's changed the way it handles that situation. So you do want to avoid having this two events trigger at the same time and act on the same object. So yes, you don't want to trigger on. Yes, it's a race condition. So somebody said it's oscillating, which is what we want. No, you're writing the value of K1. So Sharon says it shouldn't be a race condition to have the condition A less than 1 and A greater than 1 as events, because you're only reading the value of A, but you're overwriting the value of K1. I believe it would be allowed to have A. I don't know what happens. Somebody could try this. What if you make the result of the condition on A1 A equals A plus 8? I've never tried that one. I don't know whether that's allowed or not. So let me just show you this result first, and then we can explore the philosophy a bit more. I'm delighted you're coming up with all sorts of things nobody challenged me with before. It's great. So now we've got an oscillator. So I've said that there are no for loops in biology, but that doesn't mean you don't have oscillations. Here we built an oscillation through our conditions in the passage of time, even though we didn't explicitly create an oscillator. All right. Let me try this. I don't know. Let's see what happens. If I say A equals A plus 8, that's intrinsically a bad thing to do because it's going to trigger the second one. And let's just see what happens. Let's see if that by itself is legal. I don't know. Has anybody tried it? Somebody tried that and they said that it dies. Yeah, that one may cause a problem. It's not formally a race condition because at each the evaluation is done 1 microstep later, so you're not trying to do two things at the same time. But yes, you'll keep triggering it. Did anybody else try it and it failed? What if you just get rid of E2 and just say A equals A plus 8? Is that allowed? That should be allowed if you just have the first one. Darshan, does it work if you comment out the E2? What happens? Let me try that. After Darshan warns me that that's going to crash, I don't want to crash my have to restart things. So let me try this one. But it certainly does something. Rather complicated. I'm afraid I'm going to have to leave that one to you as a homework problem. A will naturally decrease. So we kick it up and then it'll decrease, and when it comes down, it'll be kicked up again. So I would expect this would be an oscillator. I think the reason it looks like it has breaks is because our time step is too big. And I want to come back to that. I just want to say that's really all the antimony methodology I wanted to teach you. And now I really do want to dig into how you connect CompuCell and antimony. I want to just refer to a couple of things. You can define units. You can say that time is minutes, concentrations are micromolar. So that's possible. That's a useful thing to do. If you're defining, you can define compartments and the volumes associated with compartments for doing physiology modeling. And there's a concept of boundary species, which is to say that you have values that are fixed, that are basically slave to things that are outside the model. Those can be either absorbing or secreting species. There are many other things you can do in antimony. Again, Herbert teaches a whole course on antimony. We can only scratch the surface, but I'm trying to cover the things that you're most likely to need when you're starting to build CompuCell models with it. So now I really want to come back and talk about how to control antimony. And people are already asking great questions because they've been looking at the code and seeing how it works. The key ideas are that integration is through Python. We can load antimony models into the entire simulation, which in case it's called a free-floating model, or into individual cells. And it's the ability to load antimony models into individual cells independently of each other that makes it so powerful. I can have the same network in every cell in 10,000 cells. So the structure of the network is the same, but the values will be different in every cell. That's very powerful. And that was something that was never thought about when SBML and antimony were developed. They never thought you'd be running multiple replicas of the same model. And there are some limitations in SBML that are annoying because of that. Something that makes life very convenient is that all antimony parameters and variables are automatically CC3D dictionary entries. I don't have to do anything to read and write to antimony. Those are available automatically as dictionary entries. That's very helpful. I do need to time step antimony by hand from Python in CompuCell. I have to time step it. And I have the ability to determine whether I'm going to solve the antimony model deterministically, as we've been doing it, or I can do it stochastically with a Gillespie solver if I want to understand molecular fluctuations. Gillespie is slow, but again, it's very powerful to do that. It's a single line change. I have rather a lot of control over the integrators. I'm typically not going to use that control. Occasionally, you'll get a strange divergence. If you ever get something that says CVODE error, that means that there are integrator problems with your antimony code. That's one that we probably won't have time to go over this week, but if people run into that, I can talk to them offline about how to deal with it. Okay, so now let's look at the code that we just ran, and it's going to be a little bit hard to see probably in the split screen. But there basically are 4 sections of that code. There's the model definition, which is the orange part. There's the list of variables in line 20 here, and my screen on the right. And then there will be a class Tellurium steppable, which is defining the loading of that model and the execution of that model. And that'll have two parts. In the start function, I load the model, and in the step function, I time step the model and do something with it. And I'll show this a little bit bigger so that it's easier to see. We know that we have to define the antimony models somewhere. And that was where we defined a string called model, which contained the antimony. It's also possible to read it from a file, and I'll show you the code for that in a minute. And it's also possible to read other model specifications, not just antimony. System biology markup language, SBML, is probably the most widely used way of specifying network models. And there's a database called Biomodels that has thousands and thousands of pre-built models in SBML. And you can load an SBML model just the way you load an antimony model. The only reason we're not using the SBML now, yes, you could build Sharon says you could build the model string programmatically. Yes, you could. And there are times when you want to do that. BioNetGen, which is a program, unfortunately, that we don't run with at the moment, not because we don't get along with them, but because they use BioNetGen is a very, very old package that takes a rule-based model specification language and turns it into SBML. And the problem is the parser they use is Perl, which is not available on Windows, and so we have a problem there. However, you can read SLML model specs, SBML model specs, or MABUS model specs, and they all work just the same. Once we've specified, yes, for programmatic development, absolutely. You might want to build conditional models, batch models, absolutely, all of these things. In those cases, you might want to write a script that generates the model external to CompuCell, and then have CompuCell read it from a file. But you definitely can change. So one thing that we didn't talk about is that events can't really change model architecture, right? We can't add a reaction to our model string with an event. We can only change parameter variables which exist already in the model. And so if we actually wanted to add a new reaction to our model, we would have to do that by editing the string. And I had students in my semester class last year or 2 years ago who did that, who actually wrote code that generated permutations of models in antimony. Because the antimony syntax is very simple, writing a little model generator is not hard. 20, 30 lines of Python, you can generate complicated combinatorial models with antimony. And the syntax is simple enough and regular enough, it's pretty easy to do that. Or modify the model based on things that happen in the CCD model. Yes, all of these are possible. Well, changing Sharon says you could change a rate constant. So changing a rate constant is easy. You don't need to change the model string to do that. And I want to come back to that in a second. That's why actually declarative model specification is so powerful. If I want, on the other hand, to have the network itself change, that's a little bit more complicated. If I anticipate that there's going to be a reaction that I might want, I can put the reaction in with a rate constant of 0 and then turn it on. But I have to anticipate, I have to have in the string all of the things that I might want to eventually use. So these are all great points that are being brought up about the possibilities. It's both powerful and a little challenging to do, but I'm pleased to see people thinking about all of these different issues. Let me just talk about the basics here, and then again we'll come back and talk about implementing things a little more sophisticated things in model 5.4, module 5.4. So once we've specified the model, we need to load it. And the evaluation of the model, the parsing of the model is only done on load. And the syntax here in the code that we've written is self.add free-floating antimony model, and then model string equals model, model name equals model, step size 1.0. In your code, it's 0.1. Somebody asked what was the difference between Tellurium v1 and v3, and Tellurium by itself was the setting of that step size. Okay, so add free-floating antimony loads a string, and free-floating means that it's running in the background of CompuCell. There's one copy for the simulation. It gives it a handle of model name. Here I called it model, which may be confusing. It loads model string from a string variable, which also is called model. I have a tendency to use the same name repeatedly, but they're actually different object classes. So model in model string is not the same as model name equals model. One is a dictionary keyword, and one is the name of a variable. And then it says that the assignment is 1 unit of antimony time is 1 unit of CompuCell time. If I said step size of 0.1, 1 unit of CompuCell time would be 0.1 units of antimony time. Okay. One thing that we will have to get used to is that because SBML was the first language we supported, you'll see things talked about as SBML models, even if they're written in Antimony or CellML or MabBoss. And so we should really, instead of saying SBML, we should have said something like network model. But if you see the word SBML, just mentally map that onto the word network. Okay. In particular, if I want to plot a value, and I'll come back to that here. Well, sorry, I've got it's on this slide too. If I wasn't going to do this quite yet, but in line 46, you'll see self.sbml.model. Model is the name model that was defined in line 30. That's the handle for the model object. SBML is a reference to any network, not just an SBML network, even an Antimony network or a CellML network too. But let's focus on this. Once I've loaded the model, I have to time step it. And so typically in my step function, I will time step that model. And the self.timestep will time step all SBML models together. So if I want multiple network models to run at different rates, I have to adjust their step sizes. There are quite a few settings for the model integrators. You can define relative tolerance, absolute tolerance, whether you want to use implicit or explicit solvers, and there's some other settings as well. I'm not going to go into those in detail today. That's one that you should look up if you need them. Then we have to be able to read and write, and that was what I was just talking about. The syntax in the little demo that I've given you is not the clearest because it's a little fancy, because we're actually using introspection in Python. So we're having VAR in line 46 is a dictionary entry, which is the name of the variable. But self.sbml.model gives me access to all of the variables and parameters that are active in that loaded antimony model. And whatever the name is in my antimony string is the keyword I use in that dictionary. So if I want, let me come down here. Maybe it's a little bit clearer. Self.SBML model quote A, close quote, will give me the value of A, the variable A that I defined. Self.SBML model keyword J1 will give me that rate that I defined for that rate equation J1. If I want to read the value, I just say something equals self.SBML.model key. If I want to write it, I just say self.SBML.model key equals new value. The one thing I have to be careful about is that there are certain things in SBML that are not writable. J1, that rate, is not writable. And so if I try to write that, I'll get an error. Somebody says we should make the time step dependent on MCS to be consistent. So yes, the reason you have that step size is to create an equivalence between the time in the Antimony model and the Monte Carlo step time. And I recommend that in your simulations, you always have a time unit declared at the beginning of the simulation. Minutes to Monte Carlo steps equals such and such. And then you put that in the very beginning of your simulation where it's a global parameter. And then everything else, all your Ks and everything else will be scaled by that. So then if you say, okay, I've changed my time, one Monte Carlo step is now half a minute or 2 minutes or 3 minutes, you have to design your program so all of that propagates down. That's a little more sophisticated than what we're doing at the moment, but it's good to think about that already as a best practice. Okay, any other questions about this now? There's a question, step size equals number of antimony iterations per MCS or involves units? Okay, so antimony has a concept of time. And it measures time in units of dimensionless number. So when antimony runs, it will microstep to get a roughly continuous derivative. The exact ways that it microsteps will depend on the settings that you define for the integrators. And so you can control that. But in this case, when you call time step SBML, if you set step size of 1, it will increment the time in antimony from 0 to 1, 1 to 2, 2 to 3. The number of actual substeps within antimony is not specified there. That's specified in the integrator settings. In general, you don't have to worry about it unless there's a numerical divergence. So yes, so it's not antimony iterations, it's the amount of time that antimony time steps is step size times MCS. That's right, antimony time units per MCS, that's exactly right. If anybody looks at the slide deck and catches a typo or makes a suggestion for ways to improve the slides, I promise you that will get included. And if you do a significant amount of that, I promise you'll get a byline, a thank you at the end of the thing for helping me edit it. Okay, so just to summarize, I haven't shown you yet that we can load antimony models into cells. I mentioned it, but the command is more or less the same. Instead of load a free-floating model, it'll be load model, and then you'll give it the cell you want to load it into, and I'll show that. Once it's loaded, the references are very symmetric. Unlike that dictionary for the whole, that shared dictionary for everything, but should have been self.dict, but wasn't. It had the the model parameters name. The naming is correct here. Self.sbml.model is the free-floating SBML, or the free-floating network model, in this case, antimony model. Cell.sbml.model is an antimony model loaded into a given cell. And so if I want to read the value, I would say instead of A equals self.sbml model, I'd read A equals cell.sbml model. And I can read and write parameters and variables, but not assigned values like J's. Any questions about that so far? Something that I haven't talked about, which I'll get to in a minute, I hope, is that you can load multiple antimony models into one cell or into the background, and they can have different time steps. You can even load them with different integrators. So you can load a deterministic model and a stochastic model into the same cell. So that's exactly, Sharon asks, can you have free-floating and cell-based models mutually exclusive or simultaneous? You can have them simultaneous. And you can have multiple independent free-floating models. You can have multiple independent models in a given cell. You can have deterministic models and stochastic models in the same cell or free-floating, which is quite powerful. There's a question, what is the difference between rate and K? And I'm not sure I understand the question. I apologize. K is a parameter value. A rate is the evaluation of the right-hand side of a rate law. I think that's what you mean. So if I say dA by dt equals something, then the thing on the right-hand side is a rate. Now, if it happens that dA by dt is constant K, then the rate constant is the rate. But in general, the K is a constant, which modifies a rate. We'll show you that in more detail. I know the terminology is a little bit confusing, and I may also not always be 100% consistent in the way I talk about it. If you catch me saying something wrong, please do correct me. Okay, so let's actually take our simulation here. And we used an event to change the rate constant. But let's do it from Python now. And so in our start function, we will load our model. And then we have to be careful because the model that I have here on the screen is different from the one that you've got on your screen now, and I have. So let's use the one that we have. So instead of saying that we're going to change the value of Ka, why don't we change the value of K1? And let's get rid of those events, all right? Since we're a little behind on time, I don't think I want to rebuild this cascade reaction quite yet. Although if you want to, we could do that, okay? Is the assignment clear? We're going to get rid of these events. And then we are going to come in, and here, after we have loaded the model, should be line 28, we're going to reassign the value here. We don't have a Ka, it'll be K1. I'll do that in front of you, and then I'll scroll back so that you can see the code. K1, I've reset here. I've gotten rid of my events. Here I load my model. And now I'm going to add a line. I have to be a little bit careful here. I don't want to be accidentally writing into, okay, that's the same. I got a blank line. So I'm going to say self.sbml model And I'm going to now have the key, which is K1. And I'm going to set that equal to, it was 0.2. I'm going to now set it to 2.0. Thank you. The danger of talking and typing at the same time. Okay, so can people try that? Try that and tell me what happens. Now I'm doing that at the very beginning, immediately after the model is loaded. But this is fairly powerful. If I had procedural code, I couldn't overwrite a value like that, because the procedural code then would reset the value. Now there are a bunch of functions built into Tellurium, like reset, that go back and read the values of parameters or variables from the original specification. That's not something you typically have to do in procedural code. But I'd like people just to try that one line 28 and see if that works for you. Crash? See what happens when I run it. Anybody else? Works fine. I'll walk through all of this again. I've got a few more things I want to do before we go to the next module. So I do want to get through these things. I don't want to rush people, but we'll get some more practice. Okay. You could also change the initial values of B and C, or change the other rate constants. For the moment, we're not going to do that. The principle, I think, it should be okay. Okay, something that is important, which we haven't talked about a lot, is stochastic solvers, Gillespie solvers in particular. So molecular reactions actually don't happen in a continuous fashion. They happen by one molecule hitting another molecule. And if concentrations of molecules are very small, then to assume that reaction rates are deterministic is not a very good approximation. The Gillespie algorithm asks the question, at each time it draws from the repertory of molecules, it asks the question, are two molecules close together? And if so, do they react? And if they react, then it does the reaction. So it moves one unit of molecule from the left-hand side to the right-hand side of the reaction. One issue with the Gillespie is that the units of molecular concentration, the units now are not concentrations. They are actually, well, not molar concentrations, which is what we're used to, typically millimolar or micromolar concentration. They're actually molecules. They're counting molecules. So the number one means one molecule in Gillespie. And so our units are different by a factor of 10 to the 23rd. So we have to remember that. On the other hand, if you're talking about something like a transcription factor binding to DNA, there's one DNA, maybe two, with that gene in it. And so to approximate that as a continuum is not a very good approximation. And for many molecular species in a cell, water, ATP, glucose, there's plenty. And assuming that there's a concentration there is fine. For many enzymes and signaling molecules, the number of copies or transcription factors, the number of copies in the whole cell may be 5 or 10, or even fewer, in which case to assume that that's a continuum is a pretty poor approximation. I'm not going to have time here to talk about where Gillespie comes from, exactly how it works, why you would want to use it. But I guarantee at some point, if you're doing molecular modeling, of networks, you'll need a stochastic solver. There are many different stochastic algorithms, but Gillespie is the most common for molecular reactions. It does sometimes have quite different effects. You may get not only quantitatively or randomly different effects, but qualitatively different effects. And it's based on the idea that two molecules have a probability of reacting that's dependent on their local densities. Because we're counting individual molecules, concentrations need to be greater than 1, and rates need to be less than 1. And so there are certain rules about Gillespie that you have to think about. So it's not instant to translate the model structure doesn't change. So our J's, our rate laws don't change when we move to Gillespie, but the parameter and the variable values do change. It's also slow because it actually does each plus minus 1 of molecular reactions independently with a bunch of random number generation. And you have to rescale the time steps. However, when we load our antimony model, we can say that we want that model to be run stochastically. And we do that by putting in the command integrator equals Gillespie. And if we want then to keep things the same, we have to change our step size. In particular, the step size has to be rescaled by the number of molecules, which is a little bit unexpected. I don't want to go into too much detail here. I suggest people come back and, if you're interested in this, look at the slide. But let us do this. So let us just run this very quickly. Go back into our simulation, change the initial value of A to 100. And then in the solver, add the command integrator equals Gillespie and run it. And tell me what it looks like. Okay. In particular, you can tell me, does it look the same in some fundamental way as what we did before? Or does it look different? So what am I asking you to do? I'm going to take A equals 10 and make it A equals 100. And then when I do all my loading of my model, I'm going to say integrator equals Gillespie. And I better check because I don't remember whether it needs a capital. It's all lowercase. Okay. Somebody got that working? Let's see what happens if I try to run that. Oh, I better get rid of that overwriting of the value of K1. Let's run it together. That was a bit fast. Let me try that again. You see A goes down and B comes up, but there's noise. A lot of fluctuations. That's for a value of 100. Now try A equals 10 for your initial condition. And run it again. What happens? Somebody tell me what's going to happen before I run it. Yes, because I'm counting molecules individually, the A and B will now be integers. And somebody says, well, the overall trajectory is the same. And that's interesting. In many cases, the overall trajectory will be the same, but not always. Let me run that again. It runs a little bit too fast to be able to see what's going on. You see if I start with 10, I get big fluctuations, but you see it's always plus minus 1, because now I'm counting individual molecules. In many cases, you will get what's called self-averaging. If I run the simulation 1,000 times and average the results, then I'll get what I would have gotten with the ODE. But not always. There are times when the stochastic model will give you fundamentally different results. In the ODE model, you never have the cell die. In the stochastic model, 10% of the time the cell dies. It's a big difference. And so it's important to have the availability of this kind of stochasticity. CompuCell, in terms of its movement of cells, is automatically stochastic. At the molecular level, it doesn't have built-in stochasticity unless you turn on Gillespie or you add stochasticity by hand. And so this is something that's worth exploring, I think. The model that we wrote earlier today, where we have the cascade reactions, actually a little prettier than the one we've got here. In the interest of time, I'll let you play with that at home. But it is quite an interesting problem to ask the question, if you run this many times, does it in fact average out to the ODE result? And you'll find that sometimes it does and sometimes it doesn't. It's model dependent. Okay. Any questions about that? I realize that there's a lot there that we're skipping. If I were teaching this in a class, it would be 3 hours on this one issue. And so all I can do here is alert you to the fact that it's an issue, and give you some guidance about where to look. Okay. It's a lot of fun to take a simulation of this kind, run a bunch of Gillespie replicas, then run it with the ODEs and see whether it averages or not. Somebody says that they have an error. Typically with the Gillespie, you'll get an error if the rate constants, if the rates are above 1. Unexpected keyword argument integrator. In that case, there's a typo in your code. We'll come back to this in a minute. I've been typing by hand, and I have some slides that would walk you through this. But I will remind you that in fact, if we are going to change these things, we should use Twedit, because Twedit knows the syntax. The network's options are rather unhelpfully hidden under the name SBML solver rather than network solver. So you have to remember, in our world, network means, SBML means network. But if you come down in Twedit to SBML solver, you will find lots and lots and lots of options. And if I come down here, the one that I want would be add antimony model . Here it is, this one. Add free-floating antimony model. If I add free-floating antimony model, it will give me a long string of things. And it will tell me all of the options that I have. And so integrator equals Gillespie is one of those options. One thing I will warn you about is that maybe the comma was missing. One of the things that I'll warn you about is that when you paste in the raw code from Twedit, it has conflicting options. It shows you all of the possible options. In particular, it'll ask you to load whether you want to load the model from a file or from a string or somewhere else. You have to select one of those. If you have all of them active at once, you'll get a crash. And so this is a case where the boilerplate code needs to be edited before you can run it. So for Wenceslaus, let me just show you on the screen the code that we need. Integrator equals quote Gillespie close quote. So let me just talk a little bit. We're a little over time, but I want to talk for another few minutes before we do a bigger exercise together. And I may skip some of the exercises later on here because we'll come back and work with them in more detail. CompuCell models can have quite complex subcellular models. So, for example, in the simulation that I've shown you, sort of the poster child for CompuCell of segmentation, we have biochemical oscillations running inside each cell. And those biochemical oscillations inside each cell, here they're written not as a network, but as ODEs. There are 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 ODEs for signaling and gene regulatory networks running inside each cell independently of each other. And then they're coupled to each other. So you can have relatively complex subcellular models. There are beautiful cell cycle models, for example, by Tyson. And if we had a little more time, I'd do an exercise where you would download the Tyson cell cycle model from the Biomodels repository, load it into CompuCell cells, have it control their growth and cell division. And this is a simulation of that. So you can actually pull the model from a library of models of cell cycle, load it into CompuCell and run it. The reason I don't want to do that is you have to edit one line of the SBML by hand. And that's a bit of an annoyance. So I don't want to do that today. The one that we're going to do a little bit later today is delta notch patterning, which is a classic developmental mechanism. In this case, we'll use a very simplified model of what's happening molecularly within the cells, and we're going to couple the cells together. And that will give rise to patterning. We talked about how the cells only know about what their local environment is and their internal state. Delta notch is a classic example of that, and that's the one I want to focus on in teaching you how to do this kind of integration. So if we want to think about this integration, the key concepts that we're going to have to deal with are how to specify the network model in the first place. Could be antimony, which is nice because it's simple text. Could be systems biology markup language, SBML, which is more or less human readable, but it's not something you want to write by hand. There are all sorts of model editor systems like Copazi for creating SBML models. There also are model editors for SLML, which is also not a language you want to read by hand. And there's Mabos. You need to be able to load these network models into the simulation or the individual cells, which we've talked about. You need to be able to time-step them, which we've talked about. You need to be able to read and write to them, which we've talked about. We need to be able to couple variables between cells. And at the moment, that's something we have to do through Python by hand. We've talked with the SBML people about designing interfaces to allow automated connection, but that's not something that's implemented in the standards. So that's something we still have to do. And then it's also possible to unload models. You can say, I don't want that model, take it out of a cell if you want to. When you do model loading, we've talked about loading a model to the background. And in this case, CompuCell does it right. in the sense that you can load something, you can load a model into all cells in your system. You can load it into all cells of a given type. You can load it into a single cell. But once it's loaded, you're free to manipulate the individual cells separately. So the scoping is only for the loading. After that, you still treat them independently. So I could load a global model. I could load a model into all cells at all. That would give me as many copies of the model as I have cells. I could load it into all cells of a given type, in which case some cells will have the model and some won't. I could load it into a single cell, in which case some cells of that type will have it and some won't. And so those are choices that we have to make. All right. This is essentially repetitive, and I don't want to go through this too much. I think in the interest of time, I don't want to come back. One of the things that I did talk about was the idea of having a time step defined in the simulation. Comment like antimony to SPML model step size. SPML step size equals conversion days to MCS. And so I strongly recommend that people use that when they build serious models, so that that's defined in the header function of your CompuCell. Sharon asks, if somebody can help Venceslas, that would be fantastic. Let's use some HiveMind to help them out. Sharon asks, so can I test if a model exists in the cell before using it? If cell.spml model equals none, I'm not sure that will work. I think that will fail. What I would recommend doing is putting the assignment in a try statement instead, so that if it fails, it doesn't crash your program. And I was going to show you that in a second. We haven't talked about, I don't think that Bobby didn't talk. Did Bobby show you try as a Python concept? I was there for most of the afternoon, but I don't remember if he did that. No. So that's something that probably we need to explain to people a little more than we've done here. I'll show you quickly. Okay. So again, just to walk you through the steps, you're going to define when you're integrating, you will define a step size conversion between the documentation. Sharon says that if cell.spml model is equals none should work. Try it. I haven't ever tried it. Please do. Report back to me whether it works. So here's my suggestions for building models. Define conversion step size, like SPML step size equals days to Monte Carlo steps, hours to Monte Carlo steps, minutes to Monte Carlo steps. Because you're free in your Antimony model to say that a time unit of 1 is 1 minute, 1 hour, 1 day. You can define the units in Antimony if you like, but otherwise it's just a number. The second thing you have to do is specify the Antimony model. And again, I recommend putting that in the header of your code, not in the step function. And Twedit will give you some helper functions for doing that. And then we will load Antimony models. And as I mentioned, there are a bunch of options. They're all present in the Python code snippets. We can load Antimony model into a single cell. We can load Antimony model into a list of cells by ID. We can load Antimony models into all cells of a given type or more than one type. We can load a free-floating Antimony model into the background. The model name will specify the handle for the model once it's loaded. So those have to be unique. If I want to load two models, I can't load them both under the handle model. One has to be model 1, model 2. Step size is the conversion from antimony time units to MCS. I can read that model from a file, in which case I'd have model file equals path instead of model string. And I can add the integrator equals Gillespie if I want. And again, you have all the options in the Python. There are a couple of other things that I can do during load. I can overwrite parameter and variable values with the initial conditions dictionary. That maybe is a little more convenient than doing them one at a time. So I could use code snippet, for example, to load a free-floating antimony model, pull down Python, SBML solver, add free-floating antimony model. It'll paste in rather long code snippet. Once I've done that, I have to decide whether I'm going to use model string or read from a file. I have to decide what the handle I'm going to use for the model is, the model name. That handle is important because I'm going to use it repeatedly, because it'll be self.handle or cell.handle. So I need to know that. And that step size, which we've talked about. Again, when I'm going to iterate the models, all the models are iterated by the single call self.timeStep. And that's why I need to be able to change the timescales for each model independently. And then I have this issue of being able to control the integrator tolerances. If I want to see what those are, there's the command self get SBML global options that'll tell me what all the possibilities are. If you run a network model and it fails, first thing you might want to do is take the network model and run it, say, in Python, not inside of CompuCell. If it runs on its own, then put it inside of CompuCell and see if it runs one step. If it runs one step, the syntax of the model is okay. And so then you probably have a divergent rate. Either something in the denominator is going to 0 or a value is going to infinity. If you don't have a divergence, reduce the step size in the simulation. And again, look for especially divide by 0 errors, which are pretty easy. It's also possible to, again, use a reserved word as a variable parameter name. If you see divergence, you have to think, is that really what you want biologically or not? If the values in your antimony change very fast, suppose over one time unit, the values change by a millionfold, then you probably are going to have to adjust the microsteps and the ratio of antimony time to CompuCell time to make that appropriate. When you do that, of course, the simulation will run slower. Simulations are controlled essentially by the fastest thing in the simulation. The faster the fastest thing you model is, the slower the simulation will be. It's possible to allow the integrators to be a little less accurate. Sometimes that helps you. And you can, in fact, by hand tell it how many microsteps to use per macro step in the integrator if you have to. Let me just walk you through the commands again in the Twedit, so you see what the Twedit looks like. In the step function, you're going to time step the SBML model. And that's always the same. It's time step SBML model and doesn't have any arguments, just self.time step SBML. Reading and writing, we've talked about. Everything is a dictionary entry. If it's in a cell, it's cell.sbml.model handle, whatever that is, quote, the variable name or parameter name. Reading and writing, we don't have to do any get or put or set. It's just a dictionary entry. We can read out the full state of the model. If we say result equals self.sbml.modelName.values, that'll return a dictionary of all of the values. Cell.sbml.modelName.values would do the same thing for a cell-loaded model. Okay. Those are all available in the pull-down menus. There are quite a few options, and so you have to look through that menu a bit to find the things you're looking for. Again, what's pasted in will be a template. You'll have to replace model name with the handle you've assigned to the model, and value name with the name of the variable or parameter you want. You can delete models, and you can copy them. When you clone a cell on division, any models that are loaded into the cell are copied automatically. That's very powerful and useful. But if I want to copy a model by hand, I can do it. I can copy an SBML simulator from one cell to another, and that will copy the model structure and the values. If I want to unload a model, for example, the cell has died and it doesn't do anything anymore, I can unload the model from an individual cell or from the background. Okay, I'm not going to run that simulation right now because we're going to do a different exercise in a few minutes. So Sharon asks, when you used SBML, self.sbml.model, that's not a built-in component of the SBML object. The model, the word model in self.sbml is intrinsic to CompuCell. The fact that it's model rather than hello world is declared when you loaded the model. So model there is the handle for the model. So it might have been more obvious if I'd called it something other than model there. No. Okay. So we're out of time for this exercise. I have some here that you can walk through, but I'd like to go on to the one that we have, the more interesting one, which is the one for delta notch. But if people have trouble, you can come back to the slide deck, which is available to you, and reference these. I realize that that's a lot to cover in a day, but I hope that the basics are clear. Basically, that the structure is not so bad. The structure is you define the model as a string or in a file. You load that model either free floating or into individual cells, and you give that model a handle. Then you read or write that model as self.sbml.handle dictionary key or cell.sbml.handle dictionary key. And then somewhere in your step function, you have to time step the model, and the amount of time in the network integrator that it runs for is given by that step size that you defined when you loaded the model. And the one other thing you have to decide is whether you're going to use an ODE solver or whether you're going to use a stochastic Gillespie solver for the model.